Hello, today I'll be talking about Bernoulli's equation demonstration for my Fluid Mechanics Lab 2. My name is Melvin Chia. So, let us get to the introduction of this experiment. So, for the introduction, the flow of a fluid has to conform with a number of scientific principles, in particular, the conservation of mass and the conservation of energy. The first of these, when applied to a liquid flowing through a conduit, requires that for a steady flow, the velocity will be inversely proportional to the flow area. The second requires that if the velocity increases, then the pressure must decrease. Bernoulli's theorem assumes that the flow is frictionless, steady, and incompressible. The objectives of this experiment today is to investigate the validity of Bernoulli's equation when it is applied to a steady flow of water through a tapered duct. As you can see here, this is the general equation for Bernoulli's principle. Next, methodology and apparatus. In this experiment, the validity of Bernoulli's equation will be verified with the use of a tapered duct connected with manometers to measure the pressure head and total head at known points along the flow. The apparatus used is an F1-10 hydraulics bench, F1-15 Bernoulli's apparatus test equipment, and a stopwatch for timing the flow measurement. As you can see here, here's the experimental setup. We have an air bleed valve, manometer tube, unions, gland nut, water inlet, and adjustable feet. Next, the procedure for this experiment is to place the ventometer onto a horizontal surface and note the height of input valve and output valve and make sure they are the same. Then attach the apparatus to the power supply, but keep the supply off and open all the air bleed valves with the manometer present at the top. Next, turn on the power supply to run the pump and adjust the flow rate control valve until water level in all the manometers is at readable range. Then, place top plug in basin and note the time required to fill the basin with a specific amount of water. Next, remove the stop plug to drain out all the water from the basin. Place the dynamic pressure probe with the static pressure pod and measure the manometer data from both of the probes. Now, place the dynamic pressure probe with the next static pressure probe and measure the manometer data from the probes. Finally, repeat the above steps for measuring data for all the manometer probes. So, as we head to the results and discussion, as you can see here, the flow area is determined, the static head from manometer is determined, the velocity is determined, the dynamic head is determined, the total head is determined, and the area for total head is determined. So, comparing with tapping 1 and tapping 11, although the value of flow area, velocity, and dynamic head is the same, the total head of tapping 1 and tapping 11 is different. The flow rate and total velocity was calculated using Bernoulli's equation. Based on the results, the velocity of the fluid is increased when it is flowing from a wider to a narrower tube as the pressure is lower at constrictions and as the pressure increases as the cross-sectional area increases. In this table, based on this graph, the decrease in area of flow decreases the height of water in the manometer column. This means they are directly proportional to each other. So in conclusion, from this experiment conducted, it was successfully demonstrated an experiment on Bernoulli's theorem. Based on the experiment, different cross-sectional areas will give different pressures and different velocity, thus changing the flow rates on each of the segments. The velocity of fluid increases as the cross-sectional area decreases. This experiment is most suitable to be used to verify Bernoulli's theorem, as the theoretical value and the experimental value calculated is not much different. There are a few errors that should be rectified, such as systemic error and random error when taking the measurements. That is all. Thank you.